Good afternoon. Today I'll be talking to you about our research on modeling diabetes mellitus, incorporating reduction in beta cells' ability to absorb blood sugar in insulin resistance, which is a joint research work of myself, Yongwimon Lenberry, Tontita Ratanakul, and Jirawan Suksamran. There have been numerous attempts to model the progression of diabetes mellitus, which is a disease suffered by those with eating disorders with prevalence in the aged population. Models in the past have not been very successful in discovering the future development of the symptoms in a long-term prediction. This is due to the fact that the state variables change in drastically different time scales. In this work, we use the singular perturbation method to analyze a model of insulin and glucose interaction proposed by the Gaetano and co-workers in 2008, which we modify to account for the decline of the ability of the cells to absorb or use up blood sugar as the glucose level becomes higher. Different dynamic behavior will be identified and numerical simulations will be carried out in support of our theoretical predictions. The Gaetano and co-workers proposed a model of the pancreatic islet compensation on which some fundamental qualitative characteristics of its solutions were proven. Its performance over the span of a lifetime is simulated under various conditions. The proposed model is judged to be a realistic and robust description of the glucose-insulin process in healthy and diabetic persons. Their model can be reduced to either fast or slow subsystems by varying the size of one of the system parameters. The original model of the Gaetano and co-workers consists of these four equations. The first one is the rate of change of beta cells mass, which varies as a product of lambda and B itself. The second equation is the rate of change of pancreas capability to increase reserved beta cells, eta. The first term here is the reduction in the capability of the pancreas due to increase in blood glucose. T sub eta is the spontaneous recovery rate of the pancreas. The third equation gives the rate of change of fasting glucose concentration G. T sub GI is the rate of liver glucose output. K sub Xg is the first order insulin independent glucose tissue uptake rate. K sub Xgi times I times G here is the second order insulin dependent glucose tissue uptake rate. The fourth equation is the rate of change of fasting insulin concentration I. The first term is the rate of insulin release from the beta cells, and the last term is the apparent first order elimination rate. According to Feldman, in a person with pre-diabetes conditions, the pancreas has to work increasingly hard to release sufficient insulin to keep the blood glucose level down. Insulin resistance occurs when excess glucose in the blood reduces the ability of the cells to absorb and use blood sugar for energy. We therefore propose a modified model to incorporate the decline in the ability of the cells in controlling plasma glucose when its level becomes higher. The modified model then consists of these four equations. where now the third equation in this model is replaced by this equation 7, where this term now varies according to the product of R and I, where R now depends on G, so that R decreases when G becomes very high. Here, epsilon and lambda are supposed to be very small. Upon observing the sizes of the parameters in the Quedado's model, we can introduce the change of variables seen here, and then dropping the primes. In the limit as lambda goes to 0, we arrive at our fast model here, where B changes very slowly, so that we can assume that its derivative is extremely small, approximately 0. So we now have these three equations, 6, 7, and 8. Since epsilon and delta are very small, eta changes very slowly, so it is a slow variable. I is then the intermediate variable. It changes at an intermediate speed. G is the fast variable, which changes at a fast speed. When we equate the right-hand side of this equation to 0, we obtain this equation. Equating the right-hand side of this equation to 0, we obtain this equation, and equating the right-hand side of this equation to 0, we obtain this equation. When we sketch the graphs of these three equations, we find three equilibrium manifolds. The blue one is the graph of the slow manifold, on which the derivative of eta is 0. The green one is a graph of the surface, where the derivative of I is 0. So it's the intermediate manifold. The red one, on which the derivative of G is 0, is the fast manifold. The slow manifold intersects the intermediate manifold along this curve. And the fast manifold, the red one, intersects the slow manifold along this curve here. These two curves then intersect each other at the point C, at which the derivatives of eta, I, and G are all 0. So it's the equilibrium point. Letting I sub m 1 or 2 be given by this expression, and I sub 1 or 2 be given as this expression, where G sub m, m1 or 2 are solutions of this cubic equation here. We can then prove the following theorem. If this inequality holds, then this curve will have two relative extrema at G sub m1 and G sub m2, which is bigger than G sub m1, both of which are positive. So this is the projection of the fast manifold onto the GI plane, and the green curve is the projection of the intermediate manifold onto the GI plane. We can then prove theorem 1, which says that if the model system of equations 6 to 8 satisfies these inequalities, and also if inequality 9 holds, then the system admits a periodic solution in the form of a limit cycle surrounding the equilibrium point C with coordinates G sub C, I sub C, and eta sub C. To prove this one, we simply consider the signs of the derivatives of G, eta, and I. Suppose we start at a generic point P. Here we'll find that derivative of G is negative. Therefore, a transition at fast speed will be made in the direction of decreasing G until the point Q is reached on the fast manifold. Here then, since the derivative of I is positive, a transition of intermediate speed will be made upward until the point I is reached, at which the stability of the manifold is lost, so that a transition of fast speed will be made until the other part of the fast manifold is reached at the point S. Here, the derivative of I is negative. So a transition of intermediate speed will be made downward until the point T is reached, at which the stability is again lost, and a transition of fast speed will be made towards this point on the other stable portion of the fast manifold. And then the transition of intermediate speed will be made again upward. And the transitions will follow on this path in the direction of decreasing eta, because here the derivative of eta is negative. Okay, so the cycling path will be made in the direction of decreasing eta until the transition reaches a point on this curve. Okay, and so the transition will be made upward to the point W, followed by a transition of fast speed to X, and then downward along this curve to Y, and a transition of fast speed will be made again back to V, which closes up the cycle, thereby forming a limit cycle or periodic solution in the three-dimensional space, as claimed by the theorem. This is the projection of this closed path onto the GI plane. Okay. You see that this happens because this curve intersects the fast manifold at the point C, which is on the part of the fast manifold which is unstable. This happens because these inequalities hold. We can also prove another theorem in the case that these inequalities hold, in which case the intermediate manifold intersects the fast manifold at this point, okay? Or if these inequalities hold, then the intermediate manifold will intersect the fast manifold. At the point, the manifold is stable. Then when the transition reaches the point V and it follows this path as before from W to X, but then when the transition is made downward here, it will reach this point. This is the case when the equilibrium point is on this side, the stable side of the fast manifold. So the transition will reach this equilibrium point. Therefore, it will cease its motion and the transition will stop here. This is then the case that the equilibrium point is stable. So we have carried out some numerical simulations of our model. This is the graph of the solution to our model system. In the case that the parameters satisfy the inequalities in theorem 1, so that the solution trajectory traces out a periodic solution or a limit cycle as predicted by the theorem. This shows the graph of G as a function of time. So it is periodic. And this is the graph of I as a function of time T, repeating itself in a periodic fashion. This is the solution trajectory in the case that the parameter satisfies the inequality in this theorem too, so that the equilibrium point is stable. Starting from this point, the trajectory traces out a curve that reaches a critical point here and stops at that point, which is a stable equilibrium point. And the time series of the three variables are seen in this graph. To conclude, in trying to efficiently control blood glucose levels, a great deal of complexity is involved in the treatment of symptoms. The use of traditional algorithm that is one size fits all may not be flexible enough and rarely considers important factors that play crucial roles in the diabetic patients. Sophisticated models can be a viable tool and should be placed at the disposal of physicians to assist them in their decision-making concerning dosage prescriptions and changing treatment protocols, which can be tailored to each patient in a personalized fashion. Thank you for your attention.